Um, well, thanks so much, Chris. Now we have Emily's. Great. Yeah, before moving to Emily, I just really liked on Margaret's presentation the schemes being publicly available, and the additional requirements aside from the standards, the ASTM standards. And Chris, it's just really nice to see a lot of those pictures and to kind of like take a deeper dive into the lab. So thanks for sharing that. Next, we have Emily McGill. She's the program director of the Compostable Field Testing Program, CFTP, a nonprofit open source international research project into how certified compostable products break down in real world composting conditions. CFTP promotes science-based answers to the challenges that compostable products face. With a Bachelor of Bioresource Engineering and a passion for collaboration, Emily takes a systemic cross-sector lens to work on solutions for a more circular and regenerative economy. She's been investigating the intersection of composting and compostable packaging since 2013. Thanks again for being here, Emily. Looking forward to what you have to share. Passing it off to you now.
Yeah, thanks for having me. It's always a pleasure to talk about the program. Jorge already introduced me. I'm the program director for the Compostable Field Testing Program. I'm calling in from Coast Salish territory in Vancouver, British Columbia, the ancestral lands of the Tsleil-Waututh, Squamish, and Musqueam people. Jorge already mentioned that we're nonprofit, open source, science-based. What he didn't emphasize is that we're really collaborative. The CFTP is a really unique research program. It was originally founded by the Compost Research and Education Foundation and BSI Biopackaging Solutions. We conceived this as a data gathering platform where any composter anywhere could field test using consistent, rigorous methods and assess the same compostable products across different sites, then report on both disintegration and composting conditions so that we can start to move beyond just lab-based testing to tease apart what leads to effective breakdown in the real world. As Christopher mentioned, field testing is just a way to check what's happening in real world facilities for items that are already proven to biodegrade, disintegrate, and not be ecotoxic through lab-based certifications. We've been field testing since 2013, and it's been a really grassroots effort, I've got to tell you. We've got support from about 14 plus additional organizations doing donations of cash, data, or in-kind time, and more than 40 composters and advisors contributing data. Now, if you haven't encountered field testing in detail before, what does it consist of? To contrast with the highly controlled lab testing we heard about, to field test, you take intact food service packaging samples, mix them with raw feedstocks, load into a compost pile or system, monitor the composting conditions like temperature, moisture, and pH and maturity. Then at the end of the composting process, we field test straight through curing as often as possible. You gather the test item residuals by sifting them through a screen, analyzing them, and then assessing the results. This is different than the lab in many ways. One of the really tangible ones is that the screen size used in the lab is 2 millimeters, but the screen size used in the field is 1/4 inch. Now, in addition to this overall process for field testing, there's actually 2 branches of the methods depending on whether you contain the test items or you load them loosely into a pile. The most common method that's been used since the 90s is the mesh bag. It allows a lot more precise disintegration results on an item by item basis, but the dose method is necessary when agitation makes mesh bags impossible, like in a lot of in-vessel systems. The mesh bag method is a lot cheaper, way lower labor costs. We've got 22 mesh bag trials and 5 dose trials under our belts, but the dose method is becoming more popular. Now, with the Compostable Field Testing Program, we are not seeking and haven't been to certify products, but to understand how disintegration varies across different compost sites. What products have we tested? Well, over the years, we've covered 82 different item types, so straws, cups, plates, bags, pouches, that cover 23 material categories, everything from PLA to PHA, paper, bagasse, wheat fiber, etc. You can loosely categorize these as, lined or unlined fiber, rigid or flexible biopolymers, and then a whole bunch of different positive controls. Now, we've had about 13 different baseline products that have been tested across many different facilities, and the rest are custom products that composters have opted to analyze. Now, although this does represent a titanic effort, we've tested over 30,000 items across, close to 30 compost sites, and methods have ranged from aerated static pile to windrow and combinations, everything in between, and sites as small as 5 tons up to over 160 tons per year. It's still a relatively small sample size given the diversity of the facilities who've participated. Each facility is as different as a fingerprint. We do need more data and more statistical significance. So take what I'm saying today as outcomes that suggest directions for future research. But let's get into the takeaways of the program so far. Firstly, compostable products do break down under the right composting conditions. Every single item that we've tested across different facilities has showed 0% residuals, aka 100% disintegration, in at least one field trial. Next, the right conditions differ greatly by material type. I'll explain this further shortly. The field test methods themselves, as I alluded to, continue to be improved and standardized. Just this year, we finally published both the contained method and the dose method under ASTM with major support from BPI over the years. And the data does reveal broad stroke recommendations for composters. We're not yet at the level of granularity that we can prescribe the ideal composting conditions for different material types, but I do think we're headed in that direction. Now, it's easy to talk about these results. We've been hearing anecdotal conclusions like this for years, but a picture says 1,000 words. Don't take my word for it. Starting with looking at a fiber product result for a compost facility that ran a test for 84 days using 5 bag replicates, the mesh bag method. This was a covered windrow facility. The top photo is day 0, the bottom photo is day 84. On the left, you have a paper box, which by and large stuck around by the end of the trial, whereas on the right, you have PLA-lined bagasse bowl that showed a pretty good disintegration trajectory. On the biopolymer side of things, and this is at the same compost facility, top you have day 0, bottom day 84, the PLA cold cup, the hot cup lid, and cutlery, all of which are PLA, which is the most commonly tested biopolymer, but different formats based on thinness, rigidity, and heat stability. They all disappeared. So what's going on? We've tested the exact same certified product across different facilities and even in the same facility and seen breakdown differ across sites and across material types. Well, you can explore the results to draw some of your own conclusions. The intention has always been to publish and open source the data. And as of 2024, you can now go to compostabletesting.org/results/explore. Let me show you what you'll see on that page. Now, CFTP is committed to transparency and making our field testing data freely accessible to the public. This is a first stab at that in a box and whisker plot. I do not want to take you back to high school math class today, but I will point out some features of the dashboard that you can explore on your own. So firstly, you can mouse over the box plot to see values. You can edit the axes, break the big blocks you see down into more specific materials or product types using the display options. And you can filter the data that's shown based on the item filters or the operation filters based on composting method, temperature, average temperatures or moisture, and then the duration. You can scroll down on that page to understand better what you're seeing with the box plots. But what I want to point out is that when you're interpreting percent residuals, which is what this graph is showing, the lower the values, the more it's broken down. So biopolymers in the center here, the yellow, have broken down more or less all the time across field trials. When you're interpreting a box and whisker plot, the wider the plot is, so the extent of the box plus the whiskers shows higher variability. So you can see that for fiber materials, there's high variability from 100% disintegration to 0%, but that more or less they're staying around. And the positive controls are all over the map. We've tested things as different as a craft paper bag, a butcher wrap, and an orange peel. So that's why. Now, why? Why this level of variability? It comes down to the question we've been asking from the beginning around composting conditions. Here's a different graph that you can't find on our website yet. This is showing temperature over time. And every line that you see on the graph is a different facility with a different field trial. This is very interesting. Compost facilities are not labs. They understandably have very different conditions between each other. The complication this presents for compostable products is that we generally see that biopolymers tend to want temperatures between 140 or over 150 to accelerate breakdown, whereas fiber really needs moderate to low temperatures and high moisture with longer durations, because the breakdown for fiber is largely driven by fungi. For all compostable products, agitation and pre-grinding helps all the materials, but it's no point asking a composter to pre-grind if they're dealing with massive amounts of contamination. So field testing has gotten us to basically confirm the anecdotal evidence that we've been hearing from composters for years. And before I close out, I do just want to reiterate that compostable packaging and all the research and certification that we're talking about today is not going to solve the problem of food waste. And even if in this dumpster bin that you can see in the film, Just Eat It, every hummus package was compostable, I still don't think that this is the best use case for compostable packaging. And so, of course, we have to be talking about reduce and reuse as well. That being said, in the limited space where compostable packaging can make a real difference, I think the most important thing to keep in mind is open source information. I think we're past the time where proprietary testing and proprietary results is going to move the dial. And so please do, if you have the capacity, share your results of your disintegration tests and your field tests. Thanks so much. If you want to know what we're up to next with the Compostable Field Testing Program, go to our site and check out the /fundraiser page, and looking forward to answering your questions.
Thanks, Emily.